Hello, my name is Dr. Blum. I'm here today to talk to you about Lewis structures in chemistry. Lewis structures are the chemical diagrams that represent the connectivity of covalent molecules. So, for example, if we're looking at water, we have the formula H2O, and it is connected with the oxygen in the middle, two hydrogens on the external, and then 4 lone electrons. And then also another example would be carbon dioxide. Which has a structure with the oxygens now on the outside and the carbon atom in the middle. So how do we decide how these molecules are put together? And that is what I'm going to talk about today in the 5 simple techniques in order to come up with a Lewis structure for any small chemical molecule. So the first step in coming up with a Lewis structure is always to determine the total available electrons. So determine the total valence, and the valence are those outer shell electrons which are involved in bonding, and I'm just going to abbreviate electrons. And so how do we do that? So in order to do that, we use the periodic table, and we can add up the valence electrons for each atom in the molecule. So on the periodic table, this is our greatest chemistry cheat sheet here. Based on the location in the periodic table, we can figure out how many valence electrons there are. So the number of valence, I've created this cheat sheet on the top with the first group has 1 valence, the second group has 2. We're not going to be dealing so much with the transition metals because when we're talking about covalent bonding, we're really interested in nonmetals, which are all over here on the periodic table. And so we're really interested in group 3. These have 3 valence. Where carbon is, they all have 4. Nitrogen has 5. Oxygen's row or column has 6. Fluorine's column has 7. And then the noble gases have 8. Except for helium. Helium only has 2 in its valence. So for a structure like water, so an example, water has 2 hydrogens. So here's hydrogen. Each one has 1. So 2 times 1. The 2 comes from the number of hydrogens. Sorry, I'll try to clarify. So that 2 is coming from that. And then 1 valence. Plus oxygen, which we see here, has 6 valence electrons, for a total of 8 available, we'll call this the available electrons. Another example, carbon dioxide. Carbon has 4. You can see that here. It's got 4. And again, oxygen, but now I have 2 of them, so 2 times 6, and therefore I have 4 plus 12, or 16 available electrons. Some cases we are looking for ions, or we're dealing with a polyatomic ion. So how do we deal with polyatomic ions? So an example here, if I have something like H3O plus, it's got a positive charge. That means I need to take away an electron. And so the total available, we'll just call that A, is equal to 3 times 1. Again, I have 3 hydrogens, each with 1 valence, plus 6. And then what that positive means, it means it has 1 less electron, so minus 1. So that gives me 9 minus 1, and so I have 8 available here. If I have a negatively charged ion, for example, in nitrate, I have 1 extra electron, and so my available is now nitrogen. We can look at the periodic table. We haven't done that one yet. Nitrogen here is in the 5 column, so 5 plus, and then oxygen is still 6, 3 times 6, and now minus electron, so plus 1 electrons available, and that gives me 5 plus 18 plus 1, which is 24. One way to know that if you be careful here is that if you end up with an odd number of available electrons, at least for a Gen Chem course, that is usually unusual. So you should add up and end up with an even number. If you have an odd number, you need to look at the charge and see if you need to adjust the number of available electrons for the charge. Now, once we know the total number of available electrons, we can then, for step 2, we're going to then sketch out the molecular structure. So when we're sketching out the molecular structure, we have to figure out which atom is going to be central. And so the central atom is the one that shows up in the middle that everything is connected to. So usually, for example, in like carbon dioxide, usually it's the first atom. It's mostly the central atom. This is usually also corresponds to the least electronegative atom. However, in cases like water, we have the chemical formula for water, hydrogen is never central. So in that case, we have to move on to the next, which is oxygen. So in this case, for water, oxygen will be our central atom. Now we can sketch our molecule. So we'll go back to sketching. And we're going to use our total available electrons in order to assist us in sketching our atom. The goal here is to make everybody happy. What do I mean by that? For everybody to be happy, they need to have a valence. And so for most atoms, the full valence is equal to 8, which is what we call an octet. There are a few exceptions to this. So one exception is hydrogen. Hydrogen has a full valence when hydrogen has 2 electrons. So hydrogen only needs 2 electrons. We can have what we call a deficient octet. And there's 2 major exceptions that don't require a full octet. And one is beryllium, which tends to only need 4 electrons, and then boron, which only needs 6 electrons. And then we can have what we call an expanded octet. And we'll explain that in a follow-up video, which means that the central atom has greater than 8 electrons, and this can happen for n equal 3 or greater. We have to have a D subshell for this to happen. Our sketching, we'll do some examples. So let's go back to water. In water, we determined that we had 8 available valence. And we also determined that oxygen was central. So the first step to sketching any Lewis structure is to attach everybody with a single bond. Because we know these things must be attached, so we must attach to a single bond. The second step is to use any remaining electrons that are not in the bond. Remember, there are 2 electrons in the bond to make everybody happy. So in water, we want to check. Hydrogen has 2 electrons in the bond, therefore hydrogen is already happy. This hydrogen is also happy because it also has 2 electrons that it's using from that bond. Oxygen at the time only has 4 from both of the bonds, but it wants 8. The good news is that right now I've used up 4 and I have 4 left over, and so we're going to put those remaining bonds, those remaining lone pairs on oxygen. And so when I do that, that makes my oxygen happy. So we always want to, after we do that, the last step in my method is always to do what I call a sanity check. And that means to make sure that I have all my 8 available electrons in my final Lewis structure. So I have 1, 2, 3, 4, 5, 6, 7, 8. So everything is happy. And that is the Lewis structure for water. We can come over here and we can look at carbon dioxide. When we came up with the available for carbon dioxide, we came up with that it had 16 available electrons. We said that carbon was central, and we're going to attach with single bonds. Again, we're going to now work from the outside in. Oxygen is not happy at this point. So oxygen needs 1, 2, 3, 4, 5, 6, and then the 2 electrons in the bond, and now it's happy. And we also have 1, 2, 3, 4, 5, 6. Now, I only had 16 electrons to start with, and now I've used up all 16 of my electrons by making the oxygen atoms happy, and I have no electrons left to make carbon happy. So carbon is sad. So how can I make carbon happy? Well, atoms can actually share up to 6 electrons, or 3 pairs up to a triple bond. And so in order to make carbon happy, oxygen can give 2 of its electrons to make a bond, a double bond with carbon. And so now carbon has 1, 2, 3, 4, 5, 6. We can do the same thing with the other oxygen. And now make a double bond with carbon and the other oxygen. And that makes our frowny face for carbon into a happy face. So now carbon has 4 electrons from the double bond, 4 electrons from this double bond, and so carbon now has 8 electrons. And oxygen has the 4 lone electrons plus the 4 in the bonds, and so each oxygen is also happy with 8 electrons. So that's how we can use multiple bonding in order to make our structures complete. I'm going to do one last example. From start to finish. So we have selenium dioxide. So the first step is to calculate the available. So we may not know right off the top of our head where selenium is on the periodic table. So let's go back. So here we are back on the periodic table. And then we can find selenium. Selenium is in the column I identified as 6. And so it has 6 valence electrons. So we'll label that as 6 for the selenium, plus 2 times 6 for each oxygen. So that's selenium, that's oxygen, and then I have the 2 of them. It's really important that you know where all these numbers come from. I'm not pulling them out of thin air. And so that gives me a total available of 18 electrons. The second step is to sketch my atom, my molecule out. And so, in general, it's not hydrogen listed first, it's selenium listed first, so we'll list selenium. And then we'll attach it to an oxygen on each side. At this point, we want to try to make everybody happy. I have no exceptions to my octet rule, so everybody here wants 8. So we'll make oxygen happy. 1, 2, 3, 4, 5, 6. And then it's got the 2 from the bond, so oxygen is happy with 8. We'll make this oxygen happy. He has 8 now. And then whatever electrons are left over is what we'll put on the central atom. So my oxygens right now use up a total of 16, including the bonds. And so that leaves me 2 to put on selenium. Again, you'll notice that selenium is unhappy because selenium at this stage only has 6 electrons. 1, 2, 3, 4, 5, 6. And so what we're going to do is we're going to move one of my oxygen atoms, a little pair, is going to end up becoming a bond and sharing with selenium. So now, when I do that, selenium should have 1, 2, 3, 4, 5, 6, 7, 8, and everyone is happy. Now, you might ask, well, why did I pick the oxygen on the left? I could have just as easily picked the oxygen on the right in order to make my double bond, and I'll put my lone pairs back here on selenium, and it would have also been happy. So which one is right? My structure A or my structure B? The truth is they're both correct, and this is a phenomenon called resonance. In this particular case, this is equivalent structures. And the true structure for selenium lies somewhere in between the structure A and the structure B. So whenever you can write more than one correct Lewis structure that meets the octet rule and meets the bonding requirements and uses up the right number of available electrons, then we end up in a phenomenon with resonance. And resonance has to have at least some form of multiple bonding. So it's really, we use this double arrow in order to represent that phenomenon. Alright, so for the next video, we're going to talk about expanded octets using this same pattern. So join me on that one. Thanks. Have a good day.